Welcome back. So today we're going to talk about one of the first effects that you've actually seen in the laboratory that requires us to think about the world in a relativistic way. And this effect is something that's known as Compton scattering. So the setup goes like this. I have an electron, and that's what we usually use when we look at Compton scattering in the lab, but I guess it could be any charged particle. And that electron is struck by a photon, and because I have the freedom to choose my coordinates, I usually line up that photon in the x direction, and I keep the electron at rest somewhere maybe in the origin of my coordinate system. But I have an electron of mass m, and it's being struck by a photon with energy E. Now, when that photon interacts with that electron, it's going to deposit some momentum and energy into that electron, right? There's going to be a momentum, there's going to be a collision. And so the final state of the system is going to be electron that is that's recoiling, right? So that's heading off in some direction. And I have a photon that's also heading off in some new direction. Now, when I actually experimentally measure this, the angle that's most important to me, and really it's most important to me because it's the easiest one to measure, is the angle of deflection of the photon. And so in the picture that I have here, my new photon, the one that's the post-collision photon, is heading away from the original incident direction by some angle theta. And the electron in this picture is then recoiling downward, but it's going to be heading off at some unknown angle. And it's actually kind of neat that I don't have to identify what this angle is before I start the problem. And as you probably have guessed from the way that we've done collisions, in relativity, sometimes I don't even have to define some of the angles, and this is one of those cases. So in my final state, both of my particles, my photon and my electron, have momentum in the x, y, and t directions. Whereas in the initial state, my electron only had momentum in the t direction, and my photon had momentum in the x and t directions. So in order to set the problem up now, I have to take all of my objects. In this case, I have four. I have my electron and photon from before the collision. I have my electron and photon from after the collision. And I have to now write down what all of those four momenta are. So before the collision, it's easy because my photon is traveling in the x direction. And so I know that the four momentum of a photon traveling in the x direction, well, the time and x components have to be equal to each other, so that way the four momentum of the photon dotted with itself is equal to 0. And therefore, I only have two entries in the four momentum of the initial photon. For the initial electron, remember, it's at rest in space, and so it's only traveling through time, and therefore the four momentum of the original electron is just given by its momentum through time, which is just E over c. The final state is a little bit more complicated. Now, I've defined the angle by which the photon has been deflected, and so I've explicitly put that in here for the four momentum of the photon, right? So the spatial part of the four momentum of the photon has E prime over c. I have an expectation that some energy has been deposited, and so the energy of the final photon isn't the same as the energy of the initial photon, but it still has an x component that's given by a cosine theta, and a y component that's given by a sine theta. The t component is still going to be E prime over c because the magnitude of the spatial part of the four momentum of a photon has to be equal to the magnitude of the temporal part of the four momentum of a photon. Now, for the four momentum of the final electron, things get a little bit more complicated. But for now, I'm just going to label it as the final energy of the electron divided by c for the time part, and then I'm going to call px and py the two spatial parts of the four momentum of the electron. Now, I'm hoping that all of the conservation laws that I have and all of the identities will make it so that I never actually have to solve for the numbers given by px and py. Of course, maybe I can at the end of the day. But the thing that we're observing in the lab is E prime, right? It's the energy of the recoiled photon, and we probably aren't even going to be able to measure the recoiled electron, right? So I'm most interested then in looking at what's happening to E prime, and that's why I've spent a little bit more time parameterizing the final momentum, the final four momentum of the final photon. Okay. I have four equations here. Now I can do a little bit of a simplification just because I remember that if I have a particle just at rest, then the rest energy, of course, right, Em is just equal to mc squared, and so I can do a quick quick substitution on the form momentum of the initial electron, and I can replace that with just mc. And now I have momenta, right? I have initial momenta and I have final momenta. And for years, what you've been doing, given a collision problem, is solving for all of the different conservation laws, all of the different conservation equations that you have from a vector equation that conserves momentum, right? In this case, it's conservation of form momentum. So in principle, you should have four equations, right? Conservation of momentum through time, conservation of momentum through each of my three spatial directions. Of course, here, nothing is happening in z, right? There's no momentum in z in the initial state, and there's no momentum in z in the final state. And so really, I just have three momentum equations, and they're actually pretty easy to write down, right? First, I could do time, right? Well, what do I have for initial time momentum? I have E over c plus mc, right? The two initial temporal momenta. And at the end, I have E prime over c plus E prime m over c, right? It's so easy, right? Relativity is hard for us to think about, but when we get down to the algebra, it turns out that all of the structures that we've been dealing with in a non-relativistic universe kind of help us to understand what's going on in the relativistic universe. In the x direction, I can do the same thing. Here, the left-hand side is a little bit easier because it's just E over c has to be equal to E prime over c cosine theta plus px. And the last one that I have to write down is y, where I have 0 on the left-hand side is equal to E prime over c sine theta plus py. And now I can do a little more algebra on this. I can solve the top equation for something, or I could solve the x and y equations for something else. We'll do that a little bit later. But basically, I want us to know that we have three equations that come just from conserving form momentum in this system, right? It's conserving it's conserving time momentum, x momentum, and y momentum. Now, if I tried to solve this for E prime, I would find out that I don't have quite enough equations, right? So as far as unknowns go, I don't know what theta is, I don't know what px is, I don't know what py is, and I don't know what E prime is. And so I need one more equation in order to fully solve this system. And that equation is not going to come from conservation of momentum, rather it's going to come from one of our fundamental ideas about special relativity. And that's that idea that I can evaluate things in different reference frames and get the same answer. In this case, the thing that I want to evaluate in different reference frames is actually the magnitude of the form momentum of the final electron, right? Because I know that if I look at that final electron, sure, in this reference frame, it's moving in the x and y directions, it's got a complicated form momentum, but in its own reference frame, well, that's a pretty easy thing to calculate. And so the magnitude of the form momentum of the final electron is just going to be m squared c squared, the way it would be in any reference frame whatsoever. And so if I take this expression, I can evaluate the left-hand side now in any reference frame, like the one in the lab, right? So I take the expression for the final form momentum of the electron, and I plug it into this expression, and I get one more algebraic relationship, and that gets me to 4 total equations, and that's going to allow me to solve for the system. And so now if I look at this expression, well, it would be nice to plug in Em prime, it would be nice to plug in Px, and it would be nice to plug in Py. Well, I can take the 3 equations that I got from conservation laws, and I can actually just solve those for those 3 things and plug them into this expression. Now, there's a little bit of algebra here, and I'm going to go through it kind of quickly, but these are the 3 expressions that I had from my conservation laws a couple of slides ago. I'm going to plug those into my equation that I get from evaluating the form momentum of the electron with itself. And there's a lot of algebra, right? So special relativity, it doesn't save us from algebra by anybody's measure. But when I plug in all of these expressions, I can do some simplification. I end up with something that looks like comparison of fractions and some interesting term on the right-hand side. And then I can simplify that to a nice expression that can actually tell me, well, what is the difference between the final state, that is, what is E prime, the energy of the final photon, compared to the energy of the initial photon. And what I find is this beautiful and non-trivial relationship between the energy of the final photon and the energy of the initial photon, which depends on the mass of the electron, right? And so this is a way of thinking about electron mass. It's a way of measuring electron mass. It's also interestingly related to 1 minus the cosine of the angle of deflection. And that's a really neat relationship, right? Because you wouldn't expect to get something like a 1 minus cosine unless there was something really interesting and relativistic going on in the physics. So, if, for example, theta is equal to 0, right? If I look for a photon that isn't deflected at all, well, then the right-hand side of this expression is 0, and the photon really hasn't deposited any energy at all into the electron. Of course, that makes sense, right? Because if the photon initial state and final state are the same, then not much has happened to the electron. And so the bigger theta gets, the bigger this effect is, and the more energy and momentum is deposited into the electron. But it's a neat and it's an unexpected answer that you get really from looking at the relativistic properties of the system. And I think that's the take-home message for Compton scattering. I mean, what we did was just an application of conservation of form momentum. There was a little bit of algebra involved, but after applying just two very simple principles of special relativity, conservation of form momentum, and then looking at the form momentum of an electron, the magnitude of the form momentum of an electron in any reference frame, I pull those things together to come up with a really neat relationship that tells me how photons and electrons interact and how they exchange energy and momentum. And that's an intrinsically and importantly and inherently relativistic statement. And that's the coolest thing about Compton scattering, is that I've really shown, if I get this relationship in the lab, that special relativity dictates how energy and momentum are exchanged between electrons and photons.